Okay, we're recording now. So 1 to 54 on the periodic table, essentially the name and the symbol. Okay, and then above that, 1 to 56, 1 to 56. And then above that, we go to 74, 76, 78 through 82, no, through 83, 86 through 88, and 92 and 94. Okay, and those I'd like you to work on the name and the symbol. So it's 1 to 56, 74, 76, 78 through 83, 86 through 88, 92 and 94. And just to remind you what the rules are, again, the first rule is, did anybody here tell me what the first rule is?
The first letter.
Very good. The first letter of the English or Latin name. English or Latin. I'm just using E or L, okay? So it's the first letter of the E or L. And if you look at these on the periodic table, what is U? Uranium, and it follows the rule. Very simple. So basically, it's just a matter of, because you will always have this handy, and you keep that in mind, it's just a matter of equating one to the other. I'm not just telling you, giving you this and saying memorize the periodic table. That's useless, because it doesn't help you think through why they're named the way they are, okay? So the key thing is first to follow the rules, and then you'll get the hang of it. The second one is the first and second letter. Okay, so what is barium? Ba, very good. Why is it not B? Because that's already taken up with boron, okay? Be is beryllium. So essentially you've got, it's sort of obvious why it fits in there. How about sodium? Na, okay? And Na is from natrum. So there's other ones in there as well related to that, like radium is Ra. Radon is the third rule, and essentially that's the first and later consonant. Okay, of English or Latin name, okay? So essentially the first and later consonant. So what is cadmium? Cd, plutonium, Pu, okay? So that would be a first and later vowel. Number 4, okay? So does everybody see the logic there, okay? And that's why these extra ones up to 56 and then all these extra ones here, almost all the elements and compounds you'll be dealing with include all these things in chemistry, okay? And then if there's some exceptions of the numbers that I don't have here, like tungsten wires talked about that goes in light bulbs. If there's some exceptions like osmium and iridium, then you'll learn them eventually. But the point is, learning these elements and symbols is the thing. So basically, I want you to know this for next Monday. Okay, but we will be covering on Thursday binary compounds, naming. Okay, so basically that'll include the elements that I'm asking you to start learning today. So you'll be starting to learn those today. And by the time we get to binary naming of compounds and the rules that go along with that, then you'll understand where we're going. Yes.
Is the quiz going to be similar to last time where we just had to know the name and symbol? That's it?
Yes, but then it'll be into compounds.
Okay.
And there'll be a bunch of things there. You're just adding an additional thing of making a compound following the rules I'm going to teach you on Thursday.
Okay.
Okay? So there's a certain logic about it that works, okay? And if you can think through it logically, you'll be able to work it out. Any questions of you virtually? Any virtual questions, people?
No.
Okay, all right, thank you. All right, so let's go to the next. Chapter. And I'm going to use a combination of PowerPoints just to go with it. I started last time with it, and what we'll do now is I'll share the screen. And what I'm going to do now is go back to Chang and finish off the things that I was talking about in here. Okay, now here we're addressing the issue of converting of Fahrenheit to degrees Celsius. And in some respects, the key thing is to go one step at a time with this, okay? Don't think of it as being asked to jump over this building. Now, how many in here, I know many of you are athletes, how many are able to do the high jump and jump from the ground floor up to the third floor? Anybody? Well, you all walked up the stairs, right? So again, if you look at a chemistry problem or even a math problem as asked to being jumped and leap tall buildings at a single bound, no, you're not asked to do that. You're asked to follow the little steps, and everybody was able to walk up the steps. Solving chemistry problems is the same thing, okay? And basically it's a matter of starting first with the rules. So let's look this as an example, and I'm going to do it with the pointer first, just so you can see where we're going with it. First, what is the first thing you need to do regarding converting Fahrenheit to degrees Celsius? Well, you got to use the conversion factor, okay? So essentially, the first thing is the conversion factor. Here, the degrees Fahrenheit is equal to 9/5 times degrees Celsius plus 32. So rearrange it, just like an algebra problem. Okay, you want to convert it, so you got to rearrange it. Okay, so essentially we do that first. How do you rearrange it? Well, you subtract 32 from both sides, right? Does everybody see that? I'm not going to write on this one. This is part of why I like these PowerPoints too. They work better. Okay, and then you do 5/9 time each side. Okay, so essentially what you've done first is you've used the variables in this. You've manipulated them out, moved them around. Now, many of you probably, while you were in high school, you may have asked, well, why am I learning this stuff? Or you might have used that worse language to say, why am I learning this junk or something, or something worse? Well, this is part of why, okay? There's a purpose for getting that kind of foundation, the variable arithmetic. Now what do you do now to solve this problem? Can anybody tell me the next step? Plug the variable in. So essentially you're going to take this number and you put it in there for the F, okay? So essentially you have degrees C is that, you plug the F in there, and then do the calculations. You do what's under this first, and then do the multiplication. Okay, so essentially you start off with that. So that's an example. Now, what I asked you to do over the weekend with those worksheets was essentially to do that many, many times. Go through the little steps. Some of you didn't need to show any work because you just use your calculator. Other times, I highly recommend you write up the work and show it. There you can figure out what your mistakes were, particularly if the units are wrong. Now, chemistry in action. Okay, you got Mars climate entered Mars atmosphere 62 miles lower than planned, was destroyed by heat. Okay, and they made a mistake there where they said that one pound, it does not equal 1 Newton. 1 pound equals 4.45 newtons. And basically the key thing is that they did not make the conversion from pounds to newtons. So the math was wrong. So essentially that's the importance of understanding the nature of mass versus weight, or doing the conversions too, because it essentially affects how these things work. Now, the next part is scientific notation, okay? And scientific notation essentially is when you have a huge number like this, 535,000, like that, that's a bit unwieldy. So essentially it's converted by doing 1, 2, 3, 1, 2, 3, 4, 5. So you take the significant figures first, 5.35 times 10 to the 5th power. Okay, so you take a number like that, you convert it in by moving with a point, and I highly recommend you use the pencil to do it first. Then you'll get the hang of it. And I believe, and most of your calculators, if you put in a number and read the manual, because it does say you can change it to exponential notation in your manual. It gives you the instructions regarding Casio or Texas Instruments, and I can show you to do it. You can put the number in, have the calculator do it for you. But the key thing is regarding it, the process is relatively straightforward. Okay, so because this is getting recorded, I can get rid of this stuff on the slide and let the other thing show you. But basically, we go to the next part. When you have 6.022 times 10 to in 12 grams of carbon, that's the definition of the mole. So it's 6.022 times 10 to the 23rd. When I was at college, it was 6.023. I don't know why they switched it, but that's how I learned it, 6.023. But in this book, it's 6.022, okay? The mass of a single carbon atom in grams is that. How would you convert that into scientific notation? You'd count and go the other way, okay? And essentially, we could do it, but I'm just gonna let go like this. Essentially, here, you have that, and go back to the pointer here. Go 1, 2, 3, etc. Go down there, and you get 1.99 times 10 to the 23rd grams for a single carbon atom. Now, does that say it's a single carbon atom with carbon 12? No, okay? It's just a general one, because essentially the AMU is calculated into that, and the weighted average is calculated into that. So essentially, the definition of a mole is exactly 12 grams of carbon 12. Okay, so that's part of what goes in there. But for the purposes of these things, it just works together. N is a number between 1 and 10, and you put the scientific, you put the other things in there. Now, this is for practice. How would you convert that? Write it down on your paper and do it for yourself first. And yes, use your pencil or your finger and move it over. Okay, so we do it. Move the decimal to the left points. How many places? 2. Very good. So you have that. And why do you use all the significant, why do you use all the numerals there? Well, in this case, they're all significant by the definition. So you have to put all of them in there. But it's always in this form, x dot yy times 10 to the z power. This is the sig figs part. Okay? Okay, here you move it to the right, you do the same thing there, and you get 7.72 times 10 to the minus 6. Addition or subtraction, you write each quantity with the same exponent. You combine n1 and n2. The exponent n remains the same. And so essentially what you have to do is get the same exponent for both of them. So you have to do a conversion there to do this. So here you have to convert this to times 10 to the fourth. So that means you move it one more to go over this. So you move it one more like that. And then you add the ones together. When you multiply n1 and n2, add the exponents together like that. You start with that and do the multiplication. And thankfully, you have calculators that you can easily do that, okay? But this is the process that's done. And then division done the same way. But again, with that, it's all about that. Significant figures, here are the rules again. We've already talked about them. And so I don't need to go through it again. But if you need practice with any of that, I highly recommend you practice. And this is where it comes into, you ask yourself the question, do I understand this, or do I need more to practice these kind of problems, okay, when you use your book and such like that. Okay, we already did that part. Accuracy and precision. These are some more things, accurate and precise, precise but not accurate, and not accurate and precise. And then the dimensional analysis method of solving problems. I went through that before. Essentially, you carry the units through the calculations. So you start with the whole thing of A times 1 equals A. And essentially, you just change the units. So if you have 35.6 feet is equal to how many centimeters? Okay, how would you do that conversion? Which conversion do you start off with? Yeah, inches. Okay, so you can do that. 35.6 feet. So let's draw the thing. So 1 foot is how many inches? 12, very good. Okay, and then you've got one more. What's the next conversion? Inch to centimeters. So you have one inch is 2.54 centimeters. The inches cancel. What are the units now? Centimeters. So your answer is probably correct. If you multiply across the top, divide by the bottom. Okay, it's very straightforward. So again, if you set it up that way, you'll be able to solve the problems very easily. And the given units cancel the design things. And so here, how many milliliters are on 1.63 liters? Conversion liter, 1 liter is 1,000 milliliters. What cancels? Liters, very good. And again, I recommend for those of you learning how to do it, do it this way. Draw the line here and then like that. People have less difficulty if you do it that way because you're less likely to flip the thing on the right when you're kind of constrained to do that. So then essentially you have those things related to that. essentially if the conversions are, if this is wrong, then essentially the units will be wrong. And that's not the correct answer. Okay, now the speed of sound in air is 343 meters per second. What is the speed in miles per hour? That's a harder problem, right? But if we set it up right, you'll understand it's really the same thing. You're just using the same steps, meters per second. And you want to convert your answer to miles per hour, right? So what are the first units you got to change? Meters to miles. So let's go 1,000 meters. Meters is 1 kilometer. And to make it simpler, 1 kilometer is 1.6 kilometers equals 1 mile. Okay, so what units cancel? The meters cancel, the kilometers cancel, you now have miles. So what's the next one you have to put in there? Seconds to minutes. So then you have 60 seconds on the top. 60 seconds is 1 minute. The seconds cancel. Now you have minutes. 60 minutes is 1 hour. Okay, minutes cancel. And now you have it in miles per hour. So essentially you now have miles per hour in the final. That gives you your answer. Okay, now let's do it neater with the let's do it neater with the conversion units, meters to miles first, and then seconds to hours. So you start off with that, converting meters to miles first. And they gave other units there, but I like to add a few more steps there to have you know 5,280 feet or 1 mile is 1.6 kilometers or something. So basically there might be something, but this is 1,609 meters, okay? So the meters cancel, then the seconds go to minutes, and minutes to hours, and then you got 760 minutes per hours there, like that, okay? So basically they do the same thing. So again, you have A equals A on both sides. The only difference is you have our units. Any questions on the other end? Okay, very good. Okay, so basically that finishes that slide. So now we'll go to the next one. And if you notice on the other slides here, essentially it has the same thing, but basically these slides, and let me show you how that works with these. These slides essentially go here. He just gives all the steps all at once instead of using the fancy animation. So I recommend you use whatever one you like better when you use these PowerPoints. And then there's a whole bunch of different examples for that one as well. Okay, so now we'll go to the next part. Okay, before I get into this, hold on a sec here. I'm gonna, okay, now before we get into that, I'm gonna go through Dalton's atomic theory. Um, Dalton, I addressed it a little bit before, and again, I like the organization of Chang here for this. We got the nice animation with this. Dalton, notice the date is in 1808. And basically, he was an early scientist coming out for what is useful for that time. And basically, a lot of the scientists, what they like to do was think about stuff. At the time in 1808, and for 200, 300, 400 years before, there was a whole thing of an issue of alchemy. Does anybody know what alchemy was? What were they trying to do? Yes. Yes, lead into gold, okay? Or they try to do other elements of the other precious things, okay? And they usually use tricks to do it, but it really wasn't gold, but it was phony gold because there's some compounds that might look goldish. And a lot of that was charlatan things. But in some respects, it's the early investigation of what can you do to make something cheap more valuable. Now, why do you think gold and silver was so valuable? Huh? Well, to create the coins, but it was so valuable because it was so uncommon. It was hard to find, okay? And that's the same thing with diamonds. If diamonds are hard to find, they're going to be more valuable and they look nice, okay? But there's a problem these days with diamonds are very easy to find because they can be manufactured now. And so basically the price is kept artificially high because of that, because they want to still have a market for it. And so in some respects, a lot of it is marketing now. But the point is with gold and silver, it has its value because of its usefulness, because of gold leaf and other stuff can be put over things and protects surfaces and makes it look nicer, like gold leaf domes that you have in the Middle East, whether it would be an old Byzantine churches or on mosques. So essentially there's a whole reason for the uses of gold and silver, whether it be cooking, jewelry, or whatever else, and basically at a value based on that. So Dalton and others were trying to come and think about what was the fundamental unit of that. And so the first one he came up with, the elements are composed of extremely small particles called atoms, okay? And this comes from the Greek word atomus. Oops. Atomus, which essentially means indivisible. Indivisible. And if you think about it, it's logical. It's very logical. His next rule was all atoms of a given element are identical, having the same mass, size, and chemical properties. The atoms of one element are different from the atoms of all other elements. And this is what he determined in 1808, because he could tell very clearly that gold was not silver and silver was not gold. They looked different, they had different properties and other stuff like that. Iron was not gold because it looked different, etc. And so basically he decided that these different metals, and that's what they were obviously looking at, because those are the pure elements that were available, that basically they were different. And so it was a natural progression from that. The next definition were compounds. And because gold, silver, and other things could be made into compounds by just reacting them, and some other metals could be burned, and other metals would react, like iron would react to make rust, and that's an obvious one. If you've got an iron bowl eventually it will rust. And so it's converting to things. And so they came up with the natural thing of compounds, where the ratio of the number of elements is present either an integer or a simple fraction. Like, for example, iron oxide is Fe2O3. So what does that say about how many irons there are? 2. How many oxygens? 3. And by definition, that is iron oxide, ferric iron oxide, okay? And you'll learn the naming a little later on in this chapter. But the big thing is you start off with the elements first, and then it goes to the compounds, and basically they're related to that. And the next one, the chemical reaction involves the separation or recombination of them, rearrangement of atoms. It does not result in their creation or destruction. So if we look at that regarding it, that is one of the laws of thermodynamics, that elements and compounds are not created or destroyed. Matter is not created or destroyed. It's merely rearranged. Okay, so in some respects, this goes hand in hand with more modern science, but that's Dalton's atomic theory. So if we look at different examples of this, carbon monoxide is this, and it has a certain name, mono, and then you got carbon dioxide, which is 2. This is called the law of multiple proportions. Okay, so for example, nitrogen could have N2O, NO, NO2, N2O4, etc. Carbon can have 2 of them. Are they going to be named the same? No, they're going to have different names. And so that later on this chapter, we'll learn how to name the different compounds based on you learning those elements that we did before, because they all start off with the element names first. Okay? And so carbon dioxide is 2 of them related to that. This is the law of multiple proportions. Okay? And that is in the book. It's not necessarily at the beginning of chapter 2, it's later on in chapter 2, but I like to introduce it in this form. Okay, so now let me delete what's on the slide again. Okay, now, for example, elements of X and then Y together goes to that, you get 8 equals X to Y. So that is a chemical reaction that takes place, and that's just the rearrangement. The elements are not created or destroyed, they merely rearrange. So if they start off separated, and then they end up going the other way. Okay, so essentially there's a whole variety of different examples of that. That is called the law of conservation of mass. Oops, let's go back. Okay, and essentially the law of conservation of mass is that in chemical reactions, okay, elements rearrange. They are not created or destroyed. And then the law of multiple proportions says that they can get you can get multiple results from it, like the carbon monoxide and carbon dioxide in the previous one. Okay, so I'm going to leave that. I'm going to leave that now and go back to the other slides here. Okay, now we're going to talk about what the elements are related to this. We'll start now with the elements. Well, the names and symbols of common elements, the Latin names from which are derived are shown in parentheses. So essentially, they're Latin names related to these things here as well. And I've already been talking about this regarding in the discussion, the Latin names have "ium" at the end. So you got calcium, and then helium, lithium, magnesium, etc. But in those cases, the Latin name is the same as the same as the English name. But in the case of sodium and others, aurum is gold, agrum is silver, sodium is natrum, but they have another name associated with it. So in a sense, it's important to understand where the symbols come from. And then with copper, you got cuprum, iron is ferrum, etc. And again, this is kind of unfortunate because the way he uses the charts and this thing, he doesn't really teach the rules that I did you. So please use my rules to help you with it. And Klein, in that Intro to Chemistry book, when it talks about naming of elements and compounds, I believe it's in chapter 4 or 5, you can refer to that also. So I encourage you to go to Hein as we reach a new chapter, and I will email you the new chapters for Hein so you can kind of get the background of it, of stuff you might have learned in high school. But the elements essentially are broken down into various places. Like here, these are the nonmetals. Over here are the metals. Okay, and essentially in here are the transition metals associated with that. And these here are the metalloids or semi-metals. And the metalloids have certain properties that is common to both the nonmetals and the metals. And there's specific reasons for that. So the periodic table is set up in a certain way with these different groups. And basically the key thing is regarding properties. Intensive properties would include the temperature and melting point, the extensive properties, length, volume, shape, etc. So intensive indicates what the element its chemical makeup is and its physical properties, whereas extensive properties are just how much you have, what is its shape and volume in those situations. And there's different examples of this too. Physical properties do not involve a change in atomic chemical makeup. Chemical properties are involved in the reaction. Now you may ask, why, Dr. Douglas, did you include that in the last quiz? Well, basically Hein covers that all very well in chapters 1 through 3. And I wanted you to think about it and put it together for yourself and see if you could come up with what a chemical change was and whatever else. And most of you did quite well, okay? So basically the quizzes will be available. I will, at the end of class, I will go get them. So if you can wait for a minute, I'll go get them and bring them back and pass them back. Those of you in virtually, you can pick them up from my office. So basically there are different elements along this and a bunch of slides showing different examples. The law of conservation of mass. Mass is neither created or destroyed in chemical reactions. And I kind of went into that again earlier in the other slides. And that is particularly important there. And then the law of definite proportions, essentially you have that, and then multiple proportions for the other things. So for example, sodium plus chlorine will go to form sodium chloride. Okay, and basically these have to be balanced, and so then we'll get into that. But the key thing is sodium chloride is always that. That's the only compound that forms with sodium chloride. That is a law of definite proportions. Okay, and that's where I'll stop today. Any questions? No, I forgot to bring them with me. The quizzes are in my office. I'll go get them right now. I'm going to stop the video. Those of you who are online, you can come pick them up from me in my office, and I'll be glad to do that with you as well. So any questions, those of you online?